Okay, so I'm not sure if this is an accident or deliberate or not, but usually for this, the A's are positive um, because of the potential problem with the root, as you can see. Now, also, if one of the A's was zero, then this becomes trivial and obvious because obviously the arithmetic mean of non-negatives is greater than or equal to zero. And likewise, if all the A's were identical, then you get the equality. So again, it's pretty trivial. So I kind of just want to focus on like this situation, really. Um, okay, so step one, uh, case n equals one. So that's the one root of a1, 1 over 1 sum a1. So that's obviously true. So that's done. Two, assume case k is true. And I think I'll just write it like this with the power 1 over k less than or equal to 1 over k, the sum ai. Three, required to prove a1 to a k plus 1, 1 over k plus 1 less than or equal to 1 over k plus 1. And then this is the sum. That was the sum up to k. This is the sum up to k plus 1 of ai. Now, the way to do this, what you can do is you can say let f(x) equal a1 up to a k x. So replace ak plus 1 with x minus 1 over k plus 1. And actually, maybe just to make it a bit clearer as well, it's a1 all the way up to ak plus then the x at the end. So that means we would be required to prove that f of a k plus 1 is, oh, did I take this the wrong way around? That's to the right. Oh, I want it as a positive, so it should be that minus that. So it should be like, let me fix that, minus here and plus here then. Okay, so I need to show that this is a positive then. Another way to do that is to show that the minimum of this function, a global minimum, is more than zero. Because like, if you can show that the global minimum is a positive, then no matter what the ak plus 1 is, then f of that would also have to be positive. So maybe we should look at finding where the minimum is. And actually, it's annoying me, so I'm going to write it the correct way around. Okay. So it is 1 over k plus 1 a1 up to ak plus x minus a1 dot 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 up to ak x 1 over k plus 1. So let's find the derivative. So the derivative here is just 1 over k plus 1. And then we bring down the power. We reduce the power by 1. One minus 1 over, sorry, okay. 1 over k plus 1 minus 1. And then we multiply by the inside derivative, a1 up to ak. So the minimum, that would be the derivative equal to 0. So then what that would mean, this is equal to 0, so the k plus 1's cancel out, and you can take this over to the left, so that a1 dot 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 ak x 1 over k plus 1 minus 1 a1 dot 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 ak, that should equal 1. So let's rearrange this a little bit. I wonder if I can clean that power up. Let me just see. 1 over k plus 1 minus k plus 1 over k plus 1. So that would be 1 minus k minus 1 over k plus 1. So that'd be minus k over k plus 1. Okay. So I could actually make that power a little bit better. Minus k over k plus 1. Okay. Right, now let's solve for x. So if I bring this underneath and then power minus 1, I'll get a1 ak x k over k plus 1 equals 1 over this, but then to the power of a minus. So it just goes back to this. I've done something wrong here. Bring down the power. Reduce the power by 1 multiplied by the inside derivative. Yeah, actually I could have simplified a Actually, I should have, to make this a little bit easier, I realized it probably would have been better to put that power inside, and then I wouldn't need to use the chain rule. Too late now. Okay. X equals a1 dot dot ak, and that's k over k plus 1, and it will be that over that, so it's 1 minus that, 1 minus k over k plus 1. Let's see what that is. That's k plus 1 over k plus 1 minus k. So that's 1 over k plus 1, funny enough. That is good, because then I can cancel that with that and then take a k root, and I get x, and I'll call it x min. Well, I don't know it's the minimum yet until I get the second derivative. That is a1 ak 1 over k. So if I calculate the second derivative, so that's gone, and that would be minus k plus 1, 1 over k plus 1 minus 1, and then a1 dot 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 ak x 1 over k plus 1 minus 1, and then it'll be a1 squared all the way up to ak squared. So that's a positive, that's a positive, that's a negative, and that's a negative. So that means that is a positive, and it's actually always a positive. And we should note that f of 0 is greater than 0, then f as it approaches infinity. I think this approaches infinity, it looks like. So in other words, it's global minimum, which is what we want. So let's calculate the second derivative at, or not the second derivative, the original function at x 0. Um, I just need to show that this is, yeah, no, sorry, not that. Um, and then actually, f a k f a k is positive. I'm getting a smidge stuck here. I'm nearly there. Um, fx0 um, mm, 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 mm. I'll have to think. I'll have to think. Okay, so now, where was I? We have to show that f of x0 is greater than or equal to 0, because then that would mean then that if the global minimum is above the x-axis, then of course that would mean f a k plus 1 would be more than or equal to 0. So let's calculate f of x0 using our definition here. So that would be 1 over k plus 1, a1 to ak plus x0, which I'll just write as x0 right now, minus, now a1 to ak, that's actually x0 power k, x0, 1 over k plus 1. And because I can use 2, then I can say that this would be more than or equal to 1 over k plus 1. And the sum of a's would be bigger than k times this. So that would be k times this, which is just actually x0 plus x0 minus x0 k plus 1, 1 over k plus 1, hang on, sorry, I don't want to mix up my brackets. Yeah, that's right. That's actually nice because they cancel. And actually, I could take k plus 1 out here and just x0, and they cancel. And that is x0 minus x0. That's equal to 0. So we've shown that this is above the x-axis, i.e. f x0 is more than or equal to 0. Whew, good. So I'm out of space. I wonder if I can just scoot this up a little bit. Okay, hang on. Okay, let's squish this right up so I can get it all on the one page. So 4, 1 plus 2 plus 3. That means it's true for n equal 1, 2, 3, etc. I just put in an example, just some values, just to give people a picture of what the graph looks like. So it's looking something like this is f, and then this here would be like x0. So we've proven that it's greater than or equal to higher than or at the x-axis. So if the minimum is above the x-axis, well, then any other point then will be above the x-axis. So that's why this is working here. And it's always convex as well, because the second derivative is a positive. So yeah, that's how it works. That's how it works. It's a bit messy, I'm afraid. It's not a nice, neat induction proof like the other ones, I'm afraid. But it is all laid out there. So just to go through the process again, the equality happens basically when all of these are the same. So I wasn't really thinking too much about equality or not equality. But the trick is to define this function and then to show that the minimum of this function is above the x-axis. And then that would necessarily lead to this result here, which is what you need to prove in the step 3 of the induction process. So it's not my most favorite proof ever, but it works.